Hello friends. So let's begin the lecture number 11 on advanced thermodynamics. So in the previous classes we had actually studied the second law of thermodynamics. We started with the Carotherius formulation that is based on the adiabatic accessibility and identified entropy as a variable that remains constant along the line that connects all points that can be reached from each other using a reversible adiabatic process, and making that a parameter which is a function of energy and x. We derived the relevant expressions that constitute the expressions for the second law of thermodynamics, as well as got formal definitions for heat and work. We found that if the universe were such that all processes there were reversible, then we could have defined interaction by contact as one in which the temperature is a generalized force and entropy is a generalized coordinate. But then unfortunately, maybe fortunately, the universe is full of all natural processes which can never be reversible, and therefore the entropy change in any process is always greater than what one sees in a reversible process because of entropy generation. So that is something that we will be talking about today, and for mathematically formalizing the second law. We also looked at the thermodynamic temperature and we actually defined a scale for thermodynamic temperature on the basis of del E by del S as the definition of temperature. So you cannot choose an arbitrary datum that we did for empirical temperature scales such as Celsius or Fahrenheit, but you'll need to actually use a more formal temperature scale which would have the datum as absolute zero temperature, where the energy of the object would diminish to zero. So that is what we looked at in the last class. So in this class, let us begin with a few more small points which are important to be understood about the second law of thermodynamics. So we'll start with the mathematical statement of the second law of thermodynamics and understand what contributes to changes in entropy during a process. And subsequently, we'll also use the second law for various corollaries, define the Carnot cycle, understand the Carnot theorem, the equivalence of the Kelvin-Planck, Clausius, and Carotherius statements of second law, and so on. So basically, to put second law in perspective, to place it in mind as familiar as the laws of thermodynamics that we had known earlier, and also clarifying any doubts and difficulties that we had about second law and entropy in the past. These small topics that we are going to cover in today's lecture and perhaps one more lecture would help. Okay. So let's move on to the PowerPoint presentation to proceed with this. So first we'll start with the mathematical statement of the second law. So we know that for a reversible process, delta Q reversible is T ds. So this is something that we obtained as for a reversible process when S is a function of, so when E is a function of S and X, so you differentiate it, you get del E by del S ds, and when the work modes are not there and you have the heat transfer which is reversible, we found that the delta Q reversible is nothing but theta ds, and we chose T and theta to be the same, so you get delta Q reversible as T ds. This is for a reversible process. But we also said that if the process is not reversible, then we'll need to add a slack variable sigma in order to make it into an equation. Otherwise, it remains as an inequality. So we know that ds is greater than delta Q for an irreversible process divided by T. So it's the same equation that we wrote here, we just brought the t here. So ds is equal to delta q reversible by t for a reversible process, and for an irreversible process the entropy change is greater than that. So we try to write these two in combined form so that you can use it for any process which is reversible or irreversible. So that we can get like this. So you write ds is equal to delta q by t plus delta sigma, where this delta sigma is a non-negative quantity. For a reversible process, this is equal to 0, so that ds equal to del q by t. That satisfies this equation. And for an irreversible process, this delta sigma is a quantity which is positive, and therefore it satisfies this equation. So ds is equal to delta q by t plus delta sigma. So delta sigma is therefore greater than or equal to 0, greater than 0 for irreversible processes and equal to 0 for reversible processes. So this term sigma is termed as the entropy generation. So you see that the change in entropy in this term is contributed to by two phenomena. One, of course, is the heat transfer, which constitutes the delta Q, and the second, which is the irreversibility, that constitutes this delta sigma, because in the absence of irreversibility this is 0, and in the absence of heat transfer this is 0. So you have a reversible and an adiabatic process. Then reversible process, this is 0, adiabatic process, this is 0. So reversible adiabatic process, both are 0, and therefore ds is 0. So that is the way you look at the second law in mathematical statement. So entropy change in a process is therefore contributed to by two phenomena. One is the heat transfer, which is shown in red here and here, and the other is irreversibility, which is shown in blue here and here. So this actually gives rise to another insight, that work done on or by an object does not by itself contribute to change in entropy of an object. Okay, so if the work is reversible, then it does not contribute to sigma, and if the work is happening that is independent of whether there is a heat transfer or not. So work interaction by itself does not contribute to the change in entropy. Only when the work transfer is irreversible, it contributes through delta sigma. Okay, so a given object, when the thermal interaction is prevented with the surroundings and it is doing work, then there is no change in entropy whatsoever. The change in entropy can happen because of the interaction by contact, that is the delta Q by T, or because of irreversibility either in the heat transfer or in the work transfer process. So that is basically the insight. So ds, or change in entropy, is contributed to by heat transfer and irreversibility. So this is one point that we need to bear in mind. Next, we also know that for a reversible process, delta Q reversible is Tds, and delta W reversible we had already seen as a summation of f prime dx prime. So from first law, you say du is equal to delta Q plus delta W. For a reversible process, it will be equal to Tds plus f prime dx prime summation. Now, since all of these are state functions, it does not depend on the path, so it does not depend on whether the process for which we are applying is reversible or irreversible. This is a state relationship. Change in internal energy can be caused by change in entropy, Tds, or the change in generalized coordinates due to the changes in generalized forces or under the influence of generalized forces. So this is a relationship between properties, and it becomes the most fundamental equation in thermodynamics. So we have seen this for applied to a compressible system, simple compressible system. So the summation goes off, there's only one work mode, and here the f prime is minus p and dx prime is dv. So we know du is equal to Tds minus p dv as the fundamental equation of thermodynamics for simple compressible systems. The same way, this can be applied to multiple work modes for different simple systems in which different work modes are present. So this equation is called the fundamental equation of thermodynamics, and it's a relationship between properties, and therefore even though when we derived it we used the reversible process, it does not depend on whether the process is reversible or irreversible, but it is a relationship between state points and properties. And so if I have a process whose path is known, I can integrate this along the path in order to obtain the changes in various properties in terms of each other. So this is one of the important salient outcomes of the mathematical statement of the second law. In one way, this is the combination of the first law and the second law, and that's why it's called the fundamental equation of thermodynamics, because we have used the second law statement in the first law and combined it together to get this statement. Now, if I apply the second law of thermodynamics to a cycle, which says ds is equal to, from the previous slide, ds is equal to delta q by t plus delta sigma. So if I apply this first law to each segment or each process in a cycle and sum it up or integrate it over the cycle, then we get this expression. The cyclic integral of ds, which will obviously be 0 because it's a state function, this will be equal to cyclic integral of del q by t plus cyclic integral of delta sigma. So this is contributed to by heat transfer in each process, and this is contributed to by irreversibility in each process. Now, since this delta sigma cyclic integral is going to be greater than or equal to 0, if it's a reversible cycle, it will be equal to 0. If it is any one process of the cycle is irreversible, even if one of the processes is irreversible, it becomes greater than 0. Then this statement, which says this plus this is equal to 0, when this is greater than or equal to 0, this has to be less than or equal to 0, and that is the classical second law statement for a cycle called the Clausius inequality. Okay, so these are the basic ingredients or mathematical statements of first law and second law, which we will be using. The mathematical statement of first law we had already seen. Delta u is equal to delta q plus delta w, delta q in plus delta w on for a process, and for a cycle it would be cyclic integral of delta q is equal to cyclic integral of delta w. Along with that, the statements of second law as we have gotten here and the fundamental equation of thermodynamics together help us in solving several problems and obtaining properties in terms of each other. Okay. So that is about the mathematical statement of the second law. Now, let's move on to the next thing. The first corollary of the second law is usually stated in terms of the Carnot cycle, because this Carnot cycle was originally conceptualized by Sadi Carnot in early to 1800s to 1900s, so early 19th century, where actually he was trying to work with the flow of caloric or the heat from a higher temperature to a lower temperature, and by that process work being generated. And that was the time when the equivalence of heat and work had not yet been established. So the Joule's experiment came about 25 years later. So the Carnot cycle was a conceptualization that Sadi Carnot had made, and that cycle is still very useful in understanding the second law and its implications to real systems. So let us look at the Carnot cycle. So if I take a power cycle in which the heat is supplied at a higher temperature TH to a cycle, and it's a sequence of 2 isothermal and 2 adiabatic processes, let's say 1, 2, 3, 4. So the process 3, 4, actually I have written I have put the numbering in a different way. The power cycle would have been 4, 3, 2, 1. It's in that order. So if 4, 3 is a process in which heat is added at a higher temperature, so that the temperature of the working substance goes from 4 to 3. The entropy of the substance goes from 4 to 3. The temperature remains TH. So the change in entropy is S2 minus S1. So the QH actually becomes equal to TH times S2 minus S1. So that is the heat added in this process. This being an isentropic process, there is no heat added. Here is a process where heat is rejected. So this QC is nothing but TC multiplied by S2 minus S1 with as the magnitude, and the direction is negative because it is lost. So that is that. So let's write QH and QC in magnitude in writing this equation. So if I apply the Clausius inequality, or rather the Yeah, Clausius inequality to this cycle. It says cyclic integral of del q by t is less than or equal to 0. So, so this should have been less than or equal to 0. So let me just make that correction right away. Yeah. Mm-hmm. Goes back 2 slides. Why is this fellow not changing? I changed it in the wrong place. This is equal to, okay, I should have changed it here. Yeah. So from the Clausius inequality, we'll get this statement as QH being coming into the system, so it's positive QH by TH is for this. Here it is 0 because Q is 0, and here it is minus QC by TC, and here it is 0. So for the cycle, if I add the Q by T or del Q by T, it gives QH by TH minus QC by TC is less than or equal to 0. So from this inequality, we'll be able to write for the Carnot cycle, this will be equal because the Carnot cycle is a reversible cycle. So its QH by TH is equal to QC by TC, and therefore 1 minus QC by QH, which is the Carnot efficiency, that is QH minus QC is the given out as the net work. So QH minus QC by QH is the efficiency of the Carnot cycle, which is 1 minus QC by QH, which will be written as 1 minus TC by TH. So this expression is strictly valid only for a Carnot cycle and cannot be used for any other cycle. That's the thing that we'll need to remember. Now, if I use the Carnot cycle as the device to measure the thermodynamic temperature, then let us say we fix Tc to be at some fixed point which is well known, like let's say the triple point of water. Then TH can be written like this. TH is equal to, so you write it as 1 minus Carnot, and then you write this, so it will be Tc divided by 1 minus eta Carnot. So if Tc is known, and if you run a Carnot cycle between this Th and Tc and get the efficiency eta Carnot, then Th will be equal to this. So you can measure any temperature by using this. Conceptually, this can be done, but in practice, the Carnot cycle cannot be constructed and operated because of the problems of reversibility or irreversibility, because we are unable to construct in practice cycles which are perfectly reversible. And therefore, this can be a theoretically tenable method for measuring the temperature, but absolute temperature cannot be measured using this. So instead, what we do is to use an ideal gas thermometer, which is a more practical device for the purpose. What is an ideal gas thermometer? Let's go to the whiteboard to explain that. So in an ideal gas thermometer, you have a bulb which is kept at a certain temperature. Okay, so the bath whose temperature is to be measured is maintained at, let us say, the temperature TH at which you are going to measure it. Now this bulb is connected to a column of let's say mercury or some such fluid, so that it's here, and you have a reservoir of the fluid so that it can be connected. Now, depending on the temperature of the gas that is inside this difference of levels would be observable. So let's say there is height h. Okay, this height h multiplied by the rho g of this density of this fluid. So rho g h will be the pressure inside this over the pressure on this side. So if this is P naught, then this will be P naught plus rho g h, where h is the distance between the two, the height difference between the two columns. Now with this, we can actually relate the pressure here to this temperature, because if the gas inside is an ideal gas, you will have P is equal to, or PV is equal to m into R into T, where R is the gas constant of the gas that is present there. So actually you can say if the volume of the bulb is kept constant, so suppose I have a mark here, and whatever temperature this goes to, I adjust this reservoir such that this level is always at this location, so that this level is free to move, then the volume inside is maintained constant. The gas trapped inside has a constant mass, so this is also a constant and this is also a constant. Then what happens? You get P is equal to some constant times T. Okay. So I can measure this. So if I have different quantities of gas inside this, I'll get different values of K, but then I'll have the same proportionality. So dP by dt will be a constant. So if I plot this with the mass of gas inside this bulb on the x-axis and the pressure here on the y-axis that I get here, for a given temperature Th, I'll find that if I change the mass here, suppose the mass is increased or mass is decreased from here, so I'll have this much pressure when the mass is this much, and when the mass is decreased, it goes here and goes here. So I can connect these three and extrapolate it to 0, where there is 0 mass, which would be the ideal gas limit. And if the gas behaves ideal in this whole range, it will be a straight line. If the gas starts behaving non-ideal, when the pressure here goes up, then it might change from linearity. Otherwise, it's this line. And if I change from one gas to another, I'll get a different line, but always all the gases will eventually. So if the R is different, if I use another gas, it might be another line, but all of these would eventually go to this. So this pressure, let us say, corresponds to the ideal gas limit of the pressure of the bulb. So this quantity will be proportional to the temperature. So if I have one value of Th, I'll have this pressure here. If I increase the temperature, then it will go somewhere here. If I increase the temperature further, it might go somewhere here, and so on. So this relationship will be maintained, and therefore I can use this pressure to maintain. Now if I look at the situation where I use an ideal gas and measure this, so this pressure and this. Now if I keep this at some standard temperature, let us say TTP, then I'll be able to get, let's say, TTP, let us say, at this location, and then any other temperature I'll be able to get at different locations. Then I'll be able to get the ratio of T by TTP. Okay, this will be equal to the pressure corresponding to the given temperature divided by the pressure corresponding to PTP. So this is a quantity that I can get from the ideal gas thermometer. So the moment I get the ratio of temperature to the temperature at any particular location, then I should be able to get a scale, because when the mass of gases here is completely reduced to 0, then we might go from here. But even that is when this is perfect vacuum. But whenever there is a certain amount of mass that is present, then you'll basically get gases, the pressure proportional to this. So suppose I correspond this to the Celsius temperature scale. That is, if I say that T boiling point minus T melting point at atmospheric temperature is 100 degrees Celsius, okay, and I have this ratio also, then I know the ratio between two temperatures. So if I say this is TTP, then this will be TTP is known to be 0.01 degrees Celsius, so this will be 99.9 degrees Celsius. So I know the temperature difference between boiling point and melting point, and if I take this boiling point and boiling point, so I have measured this quantity. So I know the ratio between the TBP and TTP, and I know the difference between these two. So I can solve for these two and obtain the values of the temperatures, in which case I get the temperatures for the boiling point and melting point on the ideal gas temperature scale as TBP is equal to, we had kept it as 100 degrees Celsius, and that comes out to 373.15, and we call it on the absolute scale. We call this absolute scale corresponding to the Celsius scale as the Kelvin scale, and TTP actually is 0.01 degrees Celsius, and that comes out to 273.16 Kelvin. So when I have the absolute scale defined, I need to define the size of one graduation, that is the difference between one graduation and the next graduation on the thermometer. So if I say that between the melting point, ice, and boiling point of water at 1 atmosphere temperature there is 100 divisions, then this difference is defined. So if I have the datum as absolute 0, and this is the melting point of ice and this is the boiling point of water, and this difference is defined as 100, then I can get what is this. So although the graduation is the same, I can have, although the scale is the same, I can have the size of the graduation different. So if the size of the graduation goes 1.8 times smaller, which is the Fahrenheit scale, then I'll be able to define the same scale with this as 32 degree Fahrenheit and this as 212 Fahrenheit. Then accordingly, this whole distance becomes some 400 and something thing, and that is in Rankine instead of the Kelvin scale. So you can have an absolute scale by defining arbitrarily the distance between any two graduations. So if it is 100, then it's the Kelvin scale. If it is 180, then it is the Rankine scale, the graduations between the melting point of ice and boiling point of water. Suppose you define any two such points and define the interval between them, then you can create a scale of your own. So long as the 0 absolute is fixed, the graduation sizes can be chosen in infinitely different ways, and therefore you can have infinitely different number of absolute scales, all of which are equivalent to each other because they will all be proportional to each other. So you will have the Kelvin scale and Rankine scale. The Kelvin temperature and Rankine temperature at the same location will always have a fixed ratio. Okay, so that is the characteristic of the temperature scale. So we'll pause at this point and resume the talk resume the discussion in the next lecture. Okay, so we'll stop here.